Hello all, welcome to the first session of PMRF NPTEL GATE classes. Today I am going to start with one question that came in GATE 2022 EC paper. We will go through the question. It is a very basic question, but we will look into the theory behind it so that we have a complete understanding of the topic that it relates to. So I am opening the question paper. So this is the question that we are going to see. Consider the circuit shown with the ideal long channel and MOSFET enhancement mode substrate which is connected to the source. The transistor is appropriately biased in the saturation region with VGG and VDD such that it acts as a linear amplifier. Vi is the small signal AC input voltage, VA and VB represent the small signal voltages at nodes A and B. We have to find the ratio of VA by VB. VA and VB rounded off to 1 decimal place. So this is a numerical answer type question. Now you can see in this question that the two resistances are given, okay, RD drain resistance and source resistance RS. Apart from this, there is no other information. The value of VDD, VGG, nothing is given. So first thing that should come into mind is whether we need the DC analysis or not. So this capital VDD, capital VGG, these are DC voltages, right? These will be used to find the DC condition of the circuit. Now in the question you see that already it is mentioned that the transistor is biased in saturation region. It acts as a linear amplifier. That means you did not find the DC condition. Okay. So there is no use of VDD, VGG, and that's why the values are not given. You did not find capital ID. Okay. Now, what is to be found? It is given that Vi is a small signal AC input and VA and VB are the corresponding small signal AC outputs, and that is the ratio of what we have to find. That means we will have to play around with the voltage gain concept. Okay, and while finding the voltage gain, the first step is to make sure that the MOSFET is biased in saturation region and it acts as a linear amplifier. That is the first step, which is already given, so we need not find it. Okay, second step is that we start finding the voltage gain of the circuit, right? So from here we will start. So I hope you have all noted down the question. I will give you 1 minute. If you have not noted down the question, please note down the question and draw the circuit. So now in the question, you can see that we have been asked to find the ratio of two voltages, that is VA and VB. Okay, so here you can see that I have drawn two circuits, circuit 1 and circuit 2, right. So here I am taking the voltage, in circuit 1 I am taking the voltage from this terminal of the MOSFET, right, and in this circuit 2 I am taking it from this terminal of MOSFET. Now considering, here you can see the VDD is applied to this terminal, and we consider that this is the terminal which is at higher potential, and therefore I consider this as the drain of the MOSFET. Similarly, this also is the drain of the MOSFET, and therefore this will be the source, right. The drain and source of the MOSFET are defined by the presence of potential. So for an NMOS, terminal with higher potential, DC, terminal with higher DC voltage becomes drain. Okay, terminal with higher DC voltage becomes drain. So now when the MOSFET's output, AC output, is taken from the drain, it is a common source configuration, right, and when it is taken out from the source, the output, when it is taken out from the source, it is common drain. I hope you have this basic idea, but still I revised this. Okay, so basically in this question the ratio of VA and VB is nothing but VA by VB is what they have asked. So they are asking you nothing but the ratio of the voltage, which is once it is taken from drain, another it is taken from source, and therefore there can be multiple approaches to solve the question. And you can see that whenever in common source, okay, so in common source, what is the voltage gain? It is GM times R out, which is nothing but RD. But what it is in the presence of source resistor, the AV turns out to be GM by 1 plus GMRS, that is the GM gets degraded by the source resistance and multiplied by RD, and therefore it is approximately equal to RD upon RS. Okay. Now in common drain configuration, the voltage gain is approximately equal to 1. Therefore, for the circuit given in question, which is this circuit, we can say that VA is equal to RD upon RS times of Vin, whereas VB is approximately equal to Vin itself, because the voltage gain is 1, right? So you can see what I have written here. This is the two circuits that I had drawn. Okay, let me zoom a little bit more, and then you see we have to find VA by VB, right? And we wrote that for VA it is in common source if you see only VA, and if you see VB, it is in common drain configuration, and from there you arrive here, and you can now see that VA by VB will nothing but RD by RS. Now here is one point that I am missing, that is when it is in common source, there is a 180 degree phase shift. So there will be a minus also present, right? So they have not asked the magnitude, they have asked the exact ratio. So you cannot miss the negative sign. Okay. So there will be minus RD by RS, which is nothing but minus 4 by 2, which is minus 2. Okay. Now this is when your in gate you have to process things very fast, and therefore you need to remember these results, right? But this is not but we need to know how we actually arrived in these equations. So we will solve the small signal model of this MOSFET, and we will see how we arrived in those two equations. Okay, how we arrived to those two equations, that we will see. But when you, for gate, especially for gate, you need to remember that in gate you have very less time and you have to solve things within that time. So you have to remember all these results, and that will only come with practice, and you have to identify what you have to do in that circuit. So when you see this circuit that was given in the exam, the first thing that you will think is that okay, only resistance values are given, I don't have any DC values options, right? No DC numbers are given, VDD, VGG, nothing is given. So finding out capital ID, DC bias current, these are all useless, because that we do to find out the biasing regions only. Those things are not to be found here. It is already given that it is in biased, in saturation region. Next thing is what they have asked. They have asked to find small signal AC input voltage, and therefore that is what is we have to do, and then we start straight away proceed with the voltage gain concept. So now I will come to the small signal model, and we will see how we arrive at the equation what we used. Okay, so let's go back. So this was the MOSFET's configuration that we used, right? And I am assuming that there is a DC bias also here, so let me write only VGG, and here there is a VDD, and this is RD, this is RS, this is round, this is round. From here we take the V out. So whatever is written in small is AC. Okay, so V in and V out. So we draw the small signal equivalent of this, and the small signal equivalent will look something like this. I am assuming that there is no channel length modulation present, so that R naught is infinity. Okay. Now here you see that the source is not at ground, but it is connected to RS, right? Here, this is the source. Okay. There is an RD connected to the drain terminal. This is the drain terminal, and V out is coming out of there. So this is how you draw the small signal model. Now you start writing the equations here. Okay. So first is that what is the voltage gain? The voltage gain is given by capital GM into R out. We'll first find capital GM. Capital GM is nothing but delta I, let's say delta ID, okay, which flows from here basically by delta Vn. Okay. So this is my GM's formula. So I'll write the KVL equation across it, which is nothing but Vn is equals to VGS plus what it will be, GM times RS into VGS, right? Is this clear? And what is ID? ID is nothing but Dm times Vgs, right? So what I am left with? I am left with Bn equals to 1 plus Gmrs into Id by Gm. This is equation 1, equation 2. From 1 and 2 you can infer that Vn equals to 1 plus Gm times Rs into Id by Gm, and therefore delta Id by delta Vn will nothing but Gm by 1 plus Gm Rs. So you see that the presence of a source resistor basically degenerates the device, that is, it decreases the value of the Gm, that is, decreases the value of the gain. Voltage gain is decreasing, right? Now what is R out here? For finding out R out, this is nothing but the Thevenin resistance. Okay, so you have to change this circuit, and what we have to do, this will be 0, this is 0 volts. So all the DC sources are shorted, this will be 0 volts here, so this is basically a short. Here I have to apply a VDC. Okay, there won't be any Vin now, no AC is present in the circuit. IDC is flowing from here. Okay, and now from here we find the output impedance. Okay, so you can apply KCL in this node and start the analysis. Okay, and you will arrive at the solution, which will basically give you R out to be the parallel equivalent of RD and R naught plus 1 plus Gm R naught into Rs. Okay, so basically I had considered R naught to be infinity here, and therefore this will be approximately equal to Rd only, since I have considered R naught to be infinity. If I don't consider R naught to be infinity, then this is the R out that we arrive at, and therefore R out will be approximately equal to Rd, and you can see that we arrive to the voltage equation which is nothing but approximately equal to, since GMRS is much greater than unity. Okay, so in GATE you will see that mostly the questions are solved by approximate equations only. Okay, because the pattern of the GATE exam is such that in a very less amount of time you have to solve the questions. So it will always be in this manner that you can actually simplify the circuit a lot. So with practice only you will be able to get this. So here I am going to stop the video, and after this we are going to take live session questions. Okay.